Hey all, um, this is another class sheet on energy, and so let's go quickly over it. And I put this file on Canvas so you can have access to it. First one, you have a force at an angle 30 degrees applied to a block. First thing to do is to do your free body diagram, and you do have your gravity force, you have your normal force, and you have this external force here. In fact, has two projections. Look at that. Is Fa cosine theta and a downward component. Downward component that is Fa sine theta. In other words, it's going to be a negative because it's a downward component. So let's see what is given. We have a given information of a mass, 56 kilograms. The distance the blocks pushed is 50 meters, and there is friction. Oops, forgot the friction. Oh, you have friction. That's your friction. And since it's moving, the friction is kinetic. On the side, you know your kinetic is equal to coefficient of kinetic friction times normal. In this case, we are dealing with a flat surface. Normal is mg. What else? Fa is given, magnitude is 250 Newton, and the coefficient of kinetic friction is also given. So this is 0.1. So what is the work done by applied force? That should be a positive work, which is given by Fa cosine 30, which is the projection of that force in x, times the displacement, which is given here, 50. The work done by gravity, don't forget that, that's the simplest one, is always given by mg, vertical displacement. In this case, vertical displacement is none. You can always see that any force that happens to be orthogonal to the displacement does no work, and that is true for the normal force too. And the work done by friction would be a negative work, which is given by the friction itself times the displacement, and that is negative knee mg times the displacement, and then you calculate that, and the net work would be given by summing up all works, all the net of all forces, or net work, and this number is going to be equal to the change in kinetic energy from where? Theorem, work kinetic energy. Okay, next one. We have a happy group of three suckers, three child, being pulled by a cord, and there is an angle of 35 degrees. This sled is moving with a constant velocity. So what constant velocity means? It means that acceleration is zero, zerovisk, which means the net force on the sled should be zero, right? That's Newton's first law. And the speed is constant, 9.35 meters per second. If the tension is given, so we have a tension of 43 newtons, determine the work done on the sled by the tension. So the work done by the tension, I know in the sled you have all kind of forces. You have the tension, right? We have friction. It has to have a friction because that thing is moving with constant velocity, and there is an upward normal reaction of the snow on the sled, which is going to your eyes now, or if you are a little bit to the left, it's to your cheek. And there is a gravity force that pulls the sled down. I'm not representing this force, but I will like this. This is gravity, Fg. It's like a dot with a circle, and No, this, I'm sorry, this is normal force. Sorry, it's a force with a circle with a dot in the center, and gravity is represented by that way. It's going down. But the work done by tension is T cosine of 35 times the displacement. And the displacement is given? No. But look what it's given. It's given the time that it takes that is led to move. Since the velocity is constant, the displacement is equal to the velocity given times the time. Okay. And the velocity is given. It's right there. Okay. Next. So in a shipping yard, a crane operator attached the cable to a shipping container, and that's the mass of it, and then use the crane to lift container vertically at constant velocity. So technically, if you do a free body diagram, this is your gravity force, this is your tension force, and 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 it goes on a distance of 34 meters. So the displacement is upward, the tension is upward, and the velocity is constant, meaning the acceleration is also zero, right? Acceleration is zero. Determine the amount of work done by each of the following. So the tension is simple, right? So you take, um, uh, because if it's moving with acceleration zero, the tension is, the magnitude is equal to Fg, which is mg. So you have an absolute value of tension. So you take the work done by tension, that shall be mg times whatever displacement that is. And the work done by gravity is negative because of the direction of gravity force. Uh, a physics TA pushes a block that has a mass of 20 kilograms. Velocity is constant, which means acceleration is zero. The distance is given down the hall. Right? The force she exerts on the car is directed at an angle. So technically, you have that, the force does 28 degrees, and the force of opposing the motion is given, so 30 newtons. The term magnitude of the force exerted on the car, so I'm not going to do this. This is simple. You guys can do it. If you can't, email me and I can work with you. How fast? This I'm not going to do either. You guys can do it. How about this one? I show in the figure below two masses. M1 is 4.8 kilograms, M2 is 80% of M1, are attached to a cord negligible mass. So which means M2 is less than M1, which means M1 will bring the system down and M2 is going to jump up. And they travel, and each travel a distance 2.8 meters, use energy content to determine the following. Speed v of the masses. So if you use energy content, do your energy table. So in your energy table, you have configuration A, which is the initial part, and configuration B, which is the final part. And then you ask which forces are, or I'm sorry, which energies are at play in this case. So we start with not B. Why did I write B? I'm getting hungry. P, G. I'm sorry. P, E, G. P, E, G. Gravitational potential energy. So you have two objects in the system, so you have to include them all together. So if you take the ground level, is the in the lowest mass, let's put that way, the ground level for PEG to be equal 0 on the lowest mass. So the block A is with respect to B at 0, right? But at point B is going to be given by M2 G times vertical displacement, which is 2.8 meters. That's at point B, right? Now, but point B at 0 has a gravitational potential energy in configuration A, which is M1G times 2.8, right? And at B is 0, right? So we have those two. So as far as gravitational potential energy, the situation is done. So do you have a spring in this problem? No, you don't. And do we have kinetic energy? Yes, we do. So at A, both of them are not moving, but at B, they both are moving with a given velocity or speed, and that should be the same for both of them because they are connected by a stout string. How about this one? 69 kilograms baseball player slides into third base. I don't know baseball, so I can't do this problem. What a third base is. He starts his slides at a speed, see if I can do it without knowing baseball, 3.9 meters per second, and his speed is 0. Oh, I see. So he starts his slides, so let's say base is the whole thing. He starts sliding here with a speed that is 3.9 meters per second, and 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 the speed is 0 when he reaches the base, which means he has a impeding force, has a friction force acting on it that will be responsible for providing a acceleration to his body that will lead to his velocity to change from 3.9 meters per second to 0 meters per second. Okay, got it. If the coefficient of friction between his clothes and surface of the baseball is given, so your coefficient is given, determine the following: mechanic energy loss during friction. So he got a hot butt doing this slide. So we want to calculate that. The mechanic energy lost. Mechanic energy lost is given by the friction force times the displacement given. That is a negative of FD. And the friction force, coefficient times mg. And so we don't have D, but we can calculate the D using Bernoulli and the conditions for the velocity, right? No, you cannot do that because you don't have distance. No, forget about Bernoulli. What you can do is to use the work kinetic energy theorem. The net work of all forces is equal to the change in kinetic energy, and the work done by all forces is this is the change in kinetic energy. Is the work of friction plus the work of gravity plus the work of normal, and normal and gravity do no work because they are perpendicular to the displacement. So the work done by friction, which is the mechanical work that is dissipated, is equal to the change in kinetic energy, and this is half mass of that person final velocity square minus the initial velocity square, which is 3.9, and this is equal to the lost, right? And then you can get your mechanical energy. Distance C slides. Now you can use now the fact that you know the work and calculate the work done by the friction is Ni mgd, this is equal to the change in kinetic energy. And then you, since you know this, you can get your distance. Uh, so looks like a problem in in um, in our homework. You have a box that slides from rest. You have an inclination. I mean, this problem is interesting. So email me, and I know some students are looking for help on it. In case you really can do it, email me and I can post a solution to this problem online. But try to do different from what the problem itself is suggesting. For instance, I could make it. I could spice out this problem and force the spring to be attached to the block as the block move up the ramp. That's a good one. I could do that. I could be evil and do this type of thing in an exam, which means when the block stops towards the end, it still has in it a potential energy of your spring, which is given by that quantity. So when you do conservation of energy, you have to include that. Okay, but I shouldn't be that evil. And let me know. Um, there is some more for fun, and I think the solutions are posted in there. Okay, good luck.